Hello all, this is Chapter 17, The Air We Breathe, Introducing the Earth's Atmosphere. We'll divide this lecture into 4 parts. First, introducing the atmosphere, its composition and its history. Second, describing atmospheric properties and structure. Third, describing precipitation and clouds. And finally, describing sources of energy and optical effects in the atmosphere. Earth's atmosphere is composed of 78% hydrogen, 21% oxygen, almost 1% argon, 0.04% CO2, and trace amounts of other gases, which are shown in the diagram on the right. So these other trace gases include CH4 or methane, O3, which is ozone, neon and helium, CO, which is carbon monoxide, among others. Water is not included in this percent calculation because it varies locally in different regions on Earth. Water occurs in the atmosphere in 3 forms: as water vapor, which is a gas in figure A in the top left, water droplets in clouds, which are liquids on figure B in the bottom left, and ice crystals in clouds in figure C in the bottom right, which are solids. So water exists in the solid, liquid, and gas state in the atmosphere and is present even when it's not visible in clouds. So sometimes you may see a blue sky and there may be some water vapor in that portion of sky. The atmosphere also contains tiny solid or liquid particles that remain suspended in the air called aerosols. Aerosols can be inorganic, like mineral dust, salts, volcanic ash, and soot, or organic, like pollen, bacteria, molds, and viruses. So we have some pictures of inorganic and organic aerosols here in the figure, with the scale bar on each photo on the bottom left representing micrometers, which is what that symbol mu stands for in front of the M. So these are very small particles imaged with something like an electron microscope. So let's name some of these aerosols. So dust can be present in vast quantities in the atmosphere. Here's an example of wind-blown dust from the Sahara Desert expanding out over the Atlantic Ocean as viewed from space. Here's an image of smoke rising from a forest fire that contributes soot to atmospheric aerosols. Photochemical smog is another group of aerosols that includes very fine particles emitted from power plants, factories, and car exhausts that are often pollutive and dangerous to human health. We will briefly discuss the evolution of Earth's atmosphere now that we understand its current composition. The stages in the evolution of the atmosphere are listed in the figure below and are typified by changing concentrations of oxygen, O2, and carbon dioxide, CO2, as time passes. So you can see in primordial Earth, the primordial atmosphere did not contain oxygen, mainly contained helium, methane, NH3, and H2. Earth's first atmosphere was comprised mainly of water, carbon dioxide, methane, and nitrogen and other elements. These were a result of volcanic activity. Earth's second atmosphere lasted until about 2.7 billion years and consisted mainly of nitrogen and carbon dioxide. and this is a result of the permanent oceans forming on Earth. Earth's third atmosphere had the beginning of increasing oxygen as a result of cyanobacteria producing it in Earth's oceans. And we fast forward all the way to today's atmosphere, where we've got more nitrogen and oxygen that support plant and animal life on Earth's surface. So these different concentrations of gases or important gases are shown in the graph on the bottom right from the Hadean to the present, with increases in O2 starting at around 2.5 billion years ago. You can see that the increase in oxygen correlates with decrease in carbon dioxide in the atmosphere. Going into more detail, Earth's first or primordial atmosphere was similar to that of solar nebulae, including hydrogen, helium, NH3, and methane. This formed as the solar wind and lunar forming collision and volcanic processes on Earth's surface changed atmospheric compositions. Earth's second atmosphere occurred at the end of the late heavy bombardment, and Earth's planetary surface cooled and began to accumulate liquid water. This was primarily nitrogen atmosphere with about 20% CO2. Earth's third atmosphere is characterized by the introduction of life and also the introduction of a specific type of life known as photosynthetic cyanobacteria that decreased carbon dioxide and increased oxygen during the Great Oxygenation event, beginning around 2.4 billion years ago. And this atmosphere was predominantly nitrogen and oxygen as it exists today. Now we'll discuss atmospheric properties in part 2 of the lecture. These include air temperature, atmospheric pressure, relative humidity, wind speed, wind direction, visibility, cloud cover, and precipitation. If someone asked you to define what is temperature, you may have a difficult time explaining it scientifically. You may say, well, whether it's hot or cold, but what does that mean in scientific terms? Well, it turns out that temperature represents the average speed at which molecules move. So air temperature represents the average speed at which molecules move in the air. The faster the average speed of the molecules, the higher the temperature. On the diagram to the right, you'll notice two thermometers with temperature scales of Fahrenheit and Celsius, which are calibrated differently. Celsius is a little bit easier to understand, where water boils at 100 degrees at sea level and water freezes at 0 degrees, also at sea level. Another temperature scale is Kelvin, and this can be converted from Celsius using the equation between the two diagrams. Atmospheric pressure is the force applied by an overlying air mass on a surface of a specified area, such as a square meter. The figure below shows a barometer, which is used to measure air pressure by meteorologists. So in this case, as air pressure decreases, the diaphragm, the red balloon or disc-shaped item in the figure, expands like a balloon, and levers cause the dial to rotate in the direction of decreasing pressure. As pressure increases, the diaphragm shrinks, and those levers cause the dial to move in the opposite direction. This is an aneroid or analog barometer. A very important concept in understanding Earth's atmosphere is that atmospheric pressure and air density decrease with increasing elevation. So about 50% of the air in the atmosphere lies below an elevation of 3.5 miles. This is shown in the figure on the right, with the red line representing atmospheric pressure. What's really nice about this figure is that not only it gives you a scale of the idea of how tall the atmosphere is and how tall landforms are on Earth, with Mount Everest being the tallest landform at about 9 or 10 kilometers. It also shows the elevation of clouds and the density of molecules in the atmosphere. So the density of molecules is closest near Earth's surface and decreases as you increase in elevation to at the point where you're above 30 kilometers above Earth's surface. There is not much air in that location. The molecules are spread extremely far out. This is one reason why it's difficult, or the reason rather, why it's difficult to breathe at higher elevations. Because when you breathe in, you need oxygen molecules to breathe. If there are less molecules in the air, there will be less oxygen molecules to go into your lungs. Relative humidity is the amount of water vapor in the air divided by the air's capacity for holding water vapor. Importantly, relative humidity varies with temperature. The warmer the air is, the more moisture it can hold. The figure below shows different size beakers representing different environments and different temperature regimes. I find this figure rather confusing, so I would prefer if you just stick to the text here to understand relative humidity. You may have heard of a term called the dew point on the Weather Channel before. The dew point is the lowest temperature in which air can be cooled before it becomes saturated. Below this temperature, there's more water than the air can hold, so it forms water droplets or frost that accumulate on solid materials on or near Earth's surface. So we see dew on grasses and leaves of bushes and trees, as well as on things like spider webs, often in the mornings, because that is the time when the temperature is the coolest during the day. Wind speed and direction are rather self-explanatory, but it is worthwhile to provide a definition of wind as an atmospheric property. So, wind is the horizontal movement of air, simply put, and wind direction is the direction from which the wind blows. Wind speed is the rate of air movement. In the picture on the right, the anemometer measures wind speed and the wind vane indicates the wind direction. Visibility is the distance from which a person with normal vision looking through the air can identify objects. Cloud cover is an estimate of how much the sky is obscured by clouds at any given time. So the figure below shows a composite satellite image of global cloud cover. Precipitation is defined as water that condenses to a solid or liquid state and falls from the sky. Precipitation rate is a measure of how fast rain, snow, or hail is falling, and total precipitation is the cumulative amount in liquid form of precipitation that fell during a specified period of time. So On the picture on the right is a rain gauge where water droplets from the rain collect in the known volume of the funnel and fall as a result of gravity down into this receptacle that drains and dips at certain points in which it becomes filled. There's an electrical device attached to the receptacle indicating every time it drains that the same volume of water has passed through the system. So this is digitized and put on a graph of amount versus time in the inset of the figure. Weather stations are sites where meteorologists have set up instruments that automatically measure atmospheric properties like temperature, dew point, wind speed, direction, visibility, cloud type and coverage, and precipitation. On the figure on the left are the North American weather stations, and the figure on the right is also an individual weather station taken from a photograph handheld camera. The major layers of the atmosphere include the troposphere, stratosphere, mesosphere, and thermosphere from the bottom up. In the troposphere, air temperature decreases with elevation. Conversely, in the stratosphere, air temperature increases with elevation, and this is a result of having a presence of ozone concentrated in the stratosphere. If you continue to go up into the mesosphere, you'll notice that air temperature decreases again with increasing elevation, and then air temperature increasing again in the thermosphere with increasing elevation. So this back and forth pattern where the change in air temperature divides the atmosphere into different layers. The troposphere, stratosphere, and mesosphere combine to create something called the homosphere, and the thermosphere is part of the heterosphere. We'll go back to this diagram. So this slide describes the mesosphere and thermosphere, and also describes the ionosphere, where there is a high concentration of charged particles or ions, which contribute to something known as the aurora, and most often observed in the wintertime in the extreme northern and southern latitudes. The picture below is the ozone layer with a large hole in it. The ozone layer in the stratosphere protects living organisms by absorbing most of the ultraviolet radiation from the sun. The hole has been caused by human activities and reduced the concentration of ozone in recent decades. I mentioned the homosphere and heterosphere a few slides ago. The homosphere is where gases in the atmosphere are well mixed. Again, this is within the troposphere, stratosphere, and mesosphere. In the heterosphere, the layers are sorted by molecular weight, and so it is not very well mixed. It is heterogeneous. Another benefit of the ionosphere is that because it contains charged ions, it allows radio waves to reflect back to Earth and thus allows radio communication across different places on Earth. Here is a picture of the auroras, which are caused by high energy particles from the sun channeled along magnetic field lines interacting with the ions in the ionosphere. This is referred to as the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. Now let's begin part 3 of the lecture on atmosphere by defining clouds. Clouds are collections of water droplets and/or tiny ice crystals suspended in the atmosphere. Clouds reflect, scatter, and absorb light. Thin clouds can appear whitish, whereas thick clouds will look gray or dark. Clouds form when saturated air cools below the dew point, and as a result, water vapor will condense on aerosols in air, forming tiny liquid water droplets, or freeze on aerosols as tiny ice crystals. So clouds literally are the result of having very, very small particles in the air, like bacteria or pollen, soot, or dust, and water as a liquid or solid adhering to those particles. Cooling happens when air rises or undergoes lifting in mechanisms we will discuss in later chapters. But there are 3 lifting mechanisms: at a front in figure A, at a mountain range in figure B, or from buoyancy due to local warming in figure C. So all of these processes come together to form clouds. This figure shows the different types of clouds that meteorologists classify based on their altitude, shape, and by whether they produce precipitation. Cumulonimbus clouds are the largest, that reach to the upper edges of the troposphere. Then there are cumulus congestus and cumulus. Then there are nimbostratus, altocumulus, cirrocumulus, cirrus, and stratus. In addition, we have altostratus and stratocumulus. As you can tell from the figures, some of these clouds form layers that are hundreds of kilometers wide. High altitude clouds are known as cirrus clouds, and they develop above elevations of 6 kilometers or 20,000 feet. These are made entirely of ice crystals, and winds cause them to form wisp-like strands. These are too high and too thin to produce precipitation. In addition to the picture of the cirrus clouds on the left, we have some cirrostratus and cirrocumulus clouds, which are, as you may imagine, a mix of cirrus and stratus and cumulus. Mid-altitude clouds form between 3 and 6 kilometers or 10,000 and 20,000 feet. These include stratus or cumulus-shaped clouds. These are also too high and thin to produce precipitation. Stratus clouds are spread out in lateral directions or XY directions, and cumulus clouds are spread out in the Z direction or in the vertical direction. Refer back to the initial figure of cloud shapes if you need to. Then there are low altitude clouds below 3 kilometers or 10,000 feet. These are the clouds that produce precipitation, and these are widespread and layered clouds and include stratus clouds. So here we've got stratocumulus and stratus. Additionally, we have towering clouds, which are not altitude defined, meaning that they occur across ranges of altitudes and can produce precipitation. These would be the cumulus clouds: cumulus, cumulus congestus, and cumulonimbus. Cumulonimbus indicates sort of lateral movement of the cumulus cloud. There are irregular or unusual clouds that take on strange shapes due to local conditions that don't fit the general categories. These would be like lenticular, wall or shelf clouds, mammatus, and roll clouds. Below is a picture of a lenticular cloud. Fog is simply when the base of a cloud occurs at Earth's surface. So there's really no difference between fog and clouds. And there are three types of fog: radiation fog, advection fog, and evaporation fog. Radiation fog forms when cooled ground absorbs heat from the air above, cooling the air just above the ground so it reaches saturation. Here's a picture as an example of radiation fog. Advection fog forms when warm, humid air flows over cooler surfaces, as would happen when warm air moves over cold ocean, water, or a field of snow. Evaporation fog forms when enough surface water evaporates into the air above it so that it becomes saturated, and this might occur over a warm lake or marsh. Now let's discuss precipitation in detail. Warm cloud precipitation is rain, and this occurs when temperatures, or rather where temperatures, stay above freezing throughout the cloud. Collision and coalescence of minuscule droplets of water occur and merge into larger drops. When drops are large enough, they have enough mass to fall out of the cloud. Cold cloud precipitation occurs when ice particles combine to form snowflakes or graupel, which are soft spheres of ice. These may fall to the ground as snow, hail, or liquid raindrops, depending on the air temperatures during precipitation as the water exits the cloud and falls to Earth's surface. So this diagram shows the microscopic aerosols, which serve as nuclei for water to accumulate on, just as in warm cloud precipitation. However, rather than water, liquid water, ice accumulates on these aerosols and forms into single crystals. Large snowflakes are aggregates of crystals, and depending on the humidity and temperature, you may form rimmed ice crystals with water on the edges, graupel, which has consistency of snowballs, and hail, which forms as extreme rimming on a graupel particle. The discussion of different types of precipitation brings us to a discussion of energy. Specifically, phase changes occur when water converts from one state to another. When phase changes occur, going from a liquid to a solid, or a solid to a liquid, or either to a gas, energy is absorbed or released, even though the temperature of the water doesn't change. The energy needed to change a phase or state is called the latent heat. So when you melt and evaporate or sublimate, you absorb latent heat, and when you condense, freeze, or deposit, you release latent heat. Another form of energy in the atmosphere is electromagnetic radiation. This form travels in the form of electric and magnetic fields through space. As light, all objects emit some electromagnetic radiation. So here we have the electromagnetic spectrum, ranging in frequencies from gamma rays, X-rays, ultraviolet rays, the visible light spectrum, to infrared, microwave, and radio waves. I always say that much of science can be boiled down into only a few diagrams. This would be one of them, in addition to something like the periodic table of the elements, helps you understand most of science of the universe. Understanding radiation in the electromagnetic spectrum of Earth's atmosphere is important for a number of reasons. One of them would be the idea of blackbody radiation, which is the idea that all the radiation a body absorbs must be re-radiated back into space, otherwise the object would continually heat up as it absorbs more energy. The warmer an object is, the more energy it emits, and the shorter the wavelength of the peak radiation. So here we have a picture of Earth's incoming solar radiation and then Earth's outgoing terrestrial long-wave radiation. We understand that there's outgoing radiation because Earth cannot continually absorb heat or radiation without emitting it as well. Well, why is this important? Visible light passes through Earth's atmosphere. As it is absorbed and re-radiates out, that wavelength changes. So think about a black asphalt sidewalk on a bright sunny day. The new and usually longer wavelengths are absorbed by the atmosphere, which acts as an insulator and traps the heat. So you can see in the diagram on the bottom that an example of shortwave radiation and longwave radiation in their ability to be absorbed by atmospheric gases. We'll turn now to a few esoteric questions. Why the sky is blue? Blue skies exist because air molecules, mainly nitrogen, cause light scattering. And this phenomenon takes place when molecules of air absorb and immediately re-emit visible light in random directions. Short wavelengths scatter light more than longer ones, so from overhead the sky looks blue, whereas from the horizon during a sunrise or sunset it will appear more red. Lastly, we'll discuss a few optical effects of the atmosphere, like mirages and inferior images. Mirage is an image formed when light reflected from an object bends through the atmosphere so that the object seems to appear where it actually doesn't exist. So this will be the case in the image on the left. Our line of sight sees an apparent image as a result of bending of light from the cool air over the hot air. An inferior mirage appears below the path of light as the light bends upward. Superior mirages appear above the path of light as the light rays are bent downward. As a result, the image is often upside down. So here we show a diagram of an inferior mirage and then an actual inferior mirage in a photograph. Sunlight passing through water droplets or ice crystals can produce a variety of colorful optical phenomena, including rainbows, as the light is refracted and reflected